Okay, hi Nadir. So we're going to talk about the third and the last chapter in chemistry, like this area of chemistry that we are studying, which was about, which is about this change of reaction, right? So to speak, like how the reaction happens. First, we discussed the reduction and oxidation aspects. Then the second thing that we were discussed was equilibrium, where we saw that there is a forward pressure and there is also a backward pressure. So maybe you don't have 100% yield in that case. You have somewhere in the middle, right? Now we are going while studying that chapter. We said the effect while studying the effect of temperature, pressure. We're discussing if the equilibrium moves to the left or the right, right? Now we want to extend. We said that when catalyst is added, the reaction does not shift to the left or the right, it just speeds up, right? It happens faster. So we said that if it's going to happen in 1 hour, it may happen in like 30 minutes, right? So this is what we're going to do now. Like that speeding up, that rate of reaction is what we're going to see now. So this is what this discussion will be about. This will be a relatively very small chapter, so let's just get on with it as quickly as possible, right? Okay. Uh, so the first thing that we want to define is what is the rate of reaction. So first of all, you want to say that rate is equal to whatever the concentration change is, right? Change of concentration of reactant or product, any one of them, right? And then that you want to see with change in time, kind of like change in distance or change in time as we do for velocity, but it's just change of concentration here. So let's look at what does that mean, right? So first of all, without going into further, the this will be the units will be moles per dm cube, which is the unit of concentration. Dm cube, remember 1 dm cube is 1 liter. We had discussed that, and 1 dm is 10 cm. So 1 dm cube is 1000 cm cube. You need to remember this in your head. Anyway, so this is the unit of concentration divided by seconds. So the whole unit will be moles per dm cube per second. So just to know what the units are. Okay. So now look at what this rate actually is. So your book kind of gives an example about this reaction about cyclopropene going into propene. So it says that at t equal to 0, they have some amount of cyclopropane and zero amount of propene, right? Which is unbelievable because there is no product that's formed, right? At 5 minutes, then you tend to measure how what is this concentration of this. You measure some value, it has of course decreased, and this one has started to increase. Similar pattern continues, this continues to decrease and this continues to increase, right? So we want to measure the change uh, of concentration with change in time, right? So we try to plot this on a graph. So we say that what is the uh, concentration of propene. So it starts from 0 and rises with time, right? uh, so then for the first 5 minutes, we say that we try to find the change in concentration by change in time. So we can just say that it will be equal to 0.27 by 5 right here, right? So change is 0.27 minus 0, and delta time is 5 minus 0. So that's kind of like finding this line right here, right? We are finding the slope of this line from here to here, which makes sense, which is what these people have done here. So, but then if we took maybe smaller, closer points, maybe we measure it every minute instead of every 5 minutes. So what we can do in that case is then we can accurately measure. We can have smaller things, and then maybe we can say what exactly is the change in concentration per change in time. So what we're kind of getting to is this idea about finding a tangent at any point. So if we say want to find uh, the what is the rate of change of concentration per time. So what is the rate at 5? So you just find the slope of the tangent at the point 5 comma this point, right? So we have done all of this in physics, of course. So here they're talking about, okay, that you want to find what is the rate of change of this. So we can also call it the instantaneous rate of change at 5 or at 10. Then you just draw a tangential line. Sorry. So we just find a tangential line, and then and then you find the slope of that line. So of course the slope can be positive or negative. In this case of cyclopropane, the concentration is decreasing, so the rate will be negative. In this sense, so this is what they find. You know how to find the slope. If you don't just like read through this, you'll remember. That's okay. So at this point, this is the one slope. Then at the another point, this is the slope. Then at this point, there is a slope. Take a guess. Pause the video and try to see whether the slope is increasing or decreasing. Right, so the slope is decreasing in magnitude. This is of a higher slope than lower, and then it finally is tending to. So we see that the rate is decreasing. Now, what they did was at every point, they have found different rates, right? So they have found, sorry, so this is the rate. So the rates as you see is decreasing. So the reason why we know that it is decreasing is 10 power minus 3 has gone to 10 power minus 4. That means it's a smaller number, right? Right. So now you have at one point, so at you have found the rate at different concentration of cyclopropane, right? You can say at 1.5 what this was the slope. At 1 this was the slope. At zero point 0.5 this was the slope. So you have three values, and then you can plot these values, the concentration with the rate. So rate here and the concentration here, and you see that it is a straight line. So this tells you that the higher the concentration of an reactant, the higher the rate. So this is what we want to remember at the end of this story. So if the concentration is higher, then the rate is higher. So this is what we saw experimentally. So if we saw that if concentration is higher, then the rate is higher. So we can also understand this by saying that, oh, so the slope of the tangent, where is it the highest in this graph? Right? It's highest at the starting point, because that is when it's the steepest, then it becomes less. Right? At the start, the concentration of cyclopropane was the highest. So it has the most amount of tendency. It is the fastest it wants to move towards its goal. After some point, the amount of cyclopropane concentration decreases, so the rate also decreases. So this is what we're talking about here. Okay. So then we talk about, so we have to understand why this is. Why is the rate proportional to this thing? So there is a theory called a collision theory that we're going to talk about. This is the only thing that we're going to talk about here. So collision theory. So collision theory. So collision theory says that rate depends on two things. So rate is proportional to number one, frequency of collisions. So if more number of, let's first talk about what collisions are, right? Like so if say you're trying to collide HCl and HH and HClCl to form molecules of HCl. So the idea is there are two kinds of collisions. So one is a collision with sufficient energy and one is a collision with insufficient energy. So when they collide, it can happen that they maybe just collide very slowly and then they go away. So in that case, no chemical reaction happens, they just bounce off each other. But if they collide with sufficient energy, then in that case, a chemical bonds might swap and break and reform. So in that case, you have an effective collision. So in this case, you see that in the A example, these are coming together with very low energy, they collide and then they go away like how they are. Right? HH bond remains in CL bond. But in the B case, you see that they come with a lot of energy. There's a BAM where this HH bond breaks, CL bond breaks, and then they form these parallel bonds, which is HCl and HCl bond, and these bonds break, and then they go on for HCl and HCl, and not HH and CL. So this is a good collision. So what we understand from this collision theory is there needs to be certain energy of the collision. So it can't happen at zero energy. You need to collide with a certain amount of energy. So it says that if the frequency of collision is higher, uh, then the rate will be higher. So if they're colliding more frequently, then it is more likely that the reaction will happen. And the second thing is, if the energy uh, of uh, of the molecules is higher, then the rate is higher. So if there, in general, if there are more energetic molecules, it is more likely that two high energy molecules will collide with each other, and which is why you will have a higher rate. So this is what you want to remember. Okay, so let's talk about a couple more things related to collision theory. So if say this is, I'm now plotting, so this is say where the reactants are. Okay, this is the time graph, and this is the enthalpy. Enthalpy, or you can say energy in a way. So energy of reactants is here, energy of products is here, right? So as time goes, oh, you can't see. Okay. So the energy of reactants is here, energy of products is here, as you can see. So we can say that as time goes on, the reaction goes from higher energy to lower energy. In this case, energy will be released. So delta H, which is H of product minus H of reactant, is negative. In this case, we know that you should always remember when delta H is negative. We studied this in the equilibrium chapter also. This means that the reaction is exothermic, right? So this reaction finally will give out heat, and we had studied this in equilibrium also, right? So collision theory tells us that it does not directly go. It first collides with a higher energy, so it needs to go somewhere at a higher energy, and then it falls back down to this energy, right? So this is that activation energy that it needs. So this is the EA. So this is that amount of extra energy that it needs to get the reaction started, to climb over the mountain, because once it is over the mountain, then the product will form. So you can imagine that if something is not of the activation energy, it tries to climb up, does not have the energy, then comes back down. So there is no reaction that happens. But then say something that with high energy it comes, then it goes up the slope, and then of course then it comes down on the slope to make the product. That is when the reaction happens. So this barrier is called activation energy right here. So we can see that for an exothermic reaction it would look like this. For an endothermic reaction, so if this is the reactant right here, so again this is enthalpy and this is time. So if this is the reactant, then the product will be higher. In this case also you would have some activation energy, and then it would finally settle to some value. So this here will again be activation energy. So reactant, and this is product. This one is an endothermic reaction. In this case, delta H is positive. Just always remember these facts. This is delta H, which is positive. Here, this is delta H, which is negative. So you need to be able to identify what EA is, what delta H is in the diagrams first. This is the first step. Okay, so let's come back to this now that we understand this. So the rate of the reaction, as said by collision theory, is dependent on two things. Once, if they collide more, then it is likely to be more, and the second thing is energy of collisions, right? So let's talk about these things in a little more detail. Okay, before that, let's talk about this graph. So what happens during a during a catalysis, when catalyst is there, right? So we say that if normally say this is the reaction that was supposed to happen, it maybe is an exothermic reaction in this case, and maybe this is what is supposed to happen in the presence of a catalyst. What happens is it starts at the same level and ends of course at the same level, but it may be through an alternate pathway. The the catalyst somehow provides a path with a lower activation energy, right? So that means the requirement for the reaction to happen will now be lower in this case. So this is the idea about for what a catalyst does. It reduces that barrier. It does not change the delta H, mind you. It still remains the same. It only changes the EA, which is now decreased. Okay, cool. So this is what it says here. Okay. So now very quickly, so let's look at two more things. The effect of concentration on the rate of reaction. So that's very simple, right? So collision theory tells us that if there are more reactions, more number of collision, then the rate of reaction will increase. So when the concentration of the reaction of the reactant is more in the solution, what do you think? The rate of reaction will be higher or lower? Higher, right? It is natural because you are packing it in, and in the same space you have more number of useful particles that can interact with each other. So you have very dense uh, situation, right, happening. So something like this, it's more likely that a red and a blue molecule will meet each other to make the reaction happen. But in this sparse medium, it is less likely, right? So the rate of reaction will be higher here. So this is the first thing that we talk about. In the case of gases, the same thing can be done with pressure. So if you increase the pressure, then those are closer together, and then the reaction then happens faster. So something like that. So this is one thing that you should know. And the second thing is, so let's talk about the other thing. The first thing that we talked about was the effect of concentration. The second thing that we talked about is, if we have to talk about, is the effect of temperature on rate of reaction, right? So the first thing is, this is, so we'll first talk about this concept called a Boltzmann distribution. So he was a very important guy in physics who talked about this distribution of energies. So it said that imagine that you have a gas or a liquid, right? And you have all these particles inside it. So they're all colliding with each other and moving with different speeds, right? So one may be moving with a slower speed, one fast particle might come and just collide with it, and then it will move with a slower speed, but then the particle that's coming in then might slow down. And all of these fast particles, there are some fast particles, there are some slow particles, right? So what Boltzmann distribution tells us is the graph, the energy of all particles. Of course, the fast particles will have more energy, and the slow particles will have more energy. So if this is the energy, and then this is the on the y-axis is the number of particles, then the graph kind of looks like what we call a bell curve, right? So the idea is that at some mean energy, you have a lot of particles average at that energy, but on the other each tail you have less particles. On the zero side you have very few particles who are not moving at all, and very few particles who are super fast, right? So the idea here is ki whoever, if particles are above this barrier of activation, so whatever this activation energy is, if they are above this barrier, then the reaction will happen. So out of all the particles that are there, if these particles collide with each other, then the reaction will happen. Otherwise, the reaction will not happen because these particles are too slow. So this is the idea, right? Now, okay, fair enough. Now the next thing that we want to understand is the effect of temperature. So temperature, say one can imagine that okay, particles start to react vigorously. So one thing is frequency of collisions increases, right? So one thing that we can conclude here is key the frequency increases. So you expect the rate of reaction to increase as frequency increases. So this is correct that when you increase the temperature, the frequency increases. But one more thing additionally happens, which also helps to increase the rate of the reaction, which we'll see. So when you have this is at a temperature T1, this graph, and maybe at a higher temperature, this graph of Boltzmann distribution kind of like looks like this. Draw that again. So you see what has happened? The peak has shifted to the right. The peak is now at a higher energy, right? The peak has shifted to right, and it looks like above this barrier of activation energy now there are more particles. So earlier there were less particles in that smaller area. So those were all these particles that are there. And now you have additionally this blue plus red area that is also there. So the number of particles have also increased. So it's not just frequency in terms of like, oh, they are moving faster. Yes, these blue particles are moving faster, but these there are additionally also these red particles that have come in, which can also now do this thing. So there is a number of particles have also increased because of Boltzmann distribution. So let me repeat what happened here. So originally you had at a temperature you had the black curve where it said that there were some particles above the activation energy which could react and make the product. But when you increase the temperature, what started happening is those particles that could make definitely were moving faster. So that increased the rate of the reaction. But additionally, what happened is your black curve shifted to the higher energy, because of which above that activation barrier, a larger number of particles could come. So now those particles, in addition to the blue particles, uh, are able to also participate in this thing. Hence, you have a higher rate of reaction because of these both of these two forces. So one general rule that your book has mentioned is that say कि for every 10-degree increase, 10 degrees centigrade increase, the rate doubles. So this is what your book talks about as a generic thing. So you increase the 10-degree and more particles come in, they move faster, and overall rate is doubled. Okay, fair enough. You can read all of this in the book. It's all mentioned. Okay, and the last thing that we want to talk about is catalysis. We said through this alternative pathway, this catalysis decreases this EA, right? So in on the Boltzmann distribution graph, this will reduce the requirement. As a result, we can see that the shaded area will be this light purple plus dark purple. So that will not increase the frequency, but it will increase the number, right? So which overall then increase the frequency, which is so overall it helps the rate of the reaction in this way by decreasing the activation energy, more particles can participate in the reaction, and hence you'll have a higher rate overall. So this is what it talks about. Okay, and the very last thing, just a theoretical point, is a homogeneous catalyst and a heterogeneous catalyst. If your catalyst is of the same physical form as your reactant. So if the reactant is a liquid, your catalyst is also a liquid, then it's of course called a homogeneous catalyst, or otherwise it's called a heterogeneous catalyst. So the example that they gave here was of hydrogen peroxide making water, making oxygen. This is an oxygen produced in reaction, and in that you put MnO2 crystals, which are these black powdery crystals that you put in hydrogen peroxide, and then the reaction goes very very fast. Earlier it go happens slow. As soon as you put MnO2, it goes very fast. And MnO2 is of course a powder. H2O2, hydrogen peroxide, is a liquid which comes in a bottle like this. So this is an example of heterogeneous catalyst. Again, it's just straightforward point, nothing too special. In terms of work, just go through the chapter. There is no nothing to do. I would say you can go through the questions as you read them. You don't need to definitely show it. Uh, and then there is also in your book there is a section about how to measure the rate of the reaction. Do definitely go through this. Once you get it, it should be fairly straightforward. This is a simple chapter. Just go through things and just make sure that you get them, and it's okay. Awesome. Okay then, cool.